Hello, everyone. Sorry for being late for 3 minutes. If somebody can tell me in the Q&A if you guys can hear me now. Okay, great. Okay, I'm gonna publish all of them. So good afternoon. Here from Waterloo. So I'm gonna just I had a few announcements before I get started. Let me go through them. First of all, as you know, labs are out. One thing about the lab right now is that it's a little bit not synced with the lectures, at least the first one. We needed memory implementation to do anything. So that's why you're doing memory management sort of at the beginning. All you need to know about the algorithms and all is in your lab manual. So there shouldn't be any problem. We'll come back to memory when we want to do memory protection. But again, we needed this part. So that's that. Hopefully from P2, it will be synced much better. The other thing is about the feedback form. I've already got some feedback. Thank you for those who shared. Please, the sooner I know what you like and what you want me to improve, the better. Don't wait until the end of the semester to share your opinion. And again, do both positive and negative because that would help me to balance between the feedback I get. Yeah, so that's pretty much it. Okay, so a recap, we were talking about virtual machine. I talked about process virtual machine, and then I started talking about system virtual machine. We talked about two types of hypervisors, type 1 and type 2. So the hypervisor of type 1 basically doesn't rely on an underlying operating system. It does hardware allocation and also virtual machine management. Type 2 hypervisors rely on an underlying operating system to do the allocation part. Now, somebody asked in the previous lecture, so I'm just reading the question, would type 1 hypervisor be used by cloud computing providers such as AWS, EC2? Seems like type 1 would have less overhead than type 2. Well, generally speaking, it could be, depending on how it's implemented. There was another question about whether or not we will come back to containers and virtual machines. Hopefully, we're going to come back to virtual machines and hypervisors. But while we're here, one example, Amazon EC2 that you asked in your question, their hypervisor is an in-house hypervisor that Amazon developed. It's called Nitro. And according to what they have released, it's actually based on KVM, and KVM is type 2 hypervisor. So it really depends on how the hypervisor is implemented when you're talking about the overheads. So something like KVM, the part that manages virtual machines is integrated inside the kernel, Linux kernel. That's why it has such a great seamless relationship with Linux, and that actually speeds up everything. So it really depends on how the hypervisor is implemented when we're talking about the performance. Hopefully I answered that question. I got another one. Both. So the question is, does the hypervisor basically just implement the hardware abstraction layer in type 2? Sort of, yes. So you're providing that abstraction layer to your virtual machines. Sorry, what was it, type 2 or type 1? Yeah. So in both of them, in both type 1 and type 2, because in your virtual machines, there is a guest operating system, there is a guest operating system running, you definitely need to provide the hardware abstraction. The operating system that is running inside the virtual machine needs to think that it's running on bare metal hardware. So we'll hopefully, fingers crossed, we'll come back to virtualization later on into the semester. Okay, so let's go. So an alternative to full system virtualization is containers. They do not provide full machine abstraction. They rely on the operating system's constructs to provide a sandbox for execution. So they use, for instance, Linux C groups, namespaces, and such to basically run their containers, if you're talking about something like Docker. So they could be run on bare metal, or they could be run atop of a virtual machine. Now, one example, so there are two types of containers. One is OS containers. These are the containers that provide virtualization to operating systems, which then those containers could run multiple processes inside them. So the examples of this is, so I can say LXC, OpenVZ, VZ, and FreeBSD jail. And then there's another one, which is the most famous one, usually used in cloud computing. It's called application containers. So these are designed to expect within the container to have only one entry point, one application, if you wish. That entry point then can spawn multiple processes, but they're just they expect to execute one process. Now, we'll just dive into this later. But then the thing about containers is that they don't actually bring up a guest operating system on top of them. They use the currently running kernel to provide everything that the applications need. So there's something between process virtualization and full system virtualization. Now, somebody asked me in the previous lecture, let me read the question. So the question was, if you run Docker on Windows or Mac, it will run the containers in a Linux VM. So that's actually an accurate description, and that does not contradict what I'm saying here. So when you launch, let's say, Dockers to run an Ubuntu image inside your Docker, what happens is that you're going to be using your host kernel to provide the virtualization, to provide services to your containers. Now, you could actually right now launch a Linux Docker inside Windows, and you might think that, oh, so what's going on? The host operating system is Windows, and I'm running Linux containers. So there is stuff going on under the hood. For instance, for the Windows case, your Docker is launching a virtual machine called Hyper-V, if I'm not mistaken, in Windows. So basically, what happens is that you're not gonna run your container. You're not gonna run your container on bare metal. You're actually running Docker on top of a virtual machine. So Hyper-V provides virtual machine that has Linux kernel, and then on top of that, you're running Docker. Okay, so I think that's that. I'm going to leave it there, and let's move on. Now, Let's talk about what makes operating systems so exciting and challenging. This is a picture, I think, from 2019, every minute of every day. And you can see really interesting numbers. So like if you look at YouTube, for instance, YouTube users watch 4,500,000 videos per minute per day, or they watched in 2019. Just look at any single one of these. These are really interesting numbers. The thing about it is that operating systems are at the heart of all of this. If you talk about cloud computing, if you talk about distributed systems, all of that. So the concepts that you will learn, hopefully in operating systems, will be used in all of those systems. Now, there are two challenges when it comes to operating systems. One is that the hardware is evolving. So we have to keep up with the hardware that is evolving, ever evolving, actually. And the complexity of our software is also ever growing. So our software, the programs that we're writing aren't getting simpler. They're actually getting more complex. And we have to keep up with both of them. If you remember that picture I showed you, we're in the middle. On top of us are applications, and the bottom is hardware. And both of them are evolving, and we want to keep up with both. And that is a little bit challenging. So we're going to see now a bunch of trends in both hardware and software to appreciate more this fact. So let's start with hardware technology trends. So for years, we have been doubling the number of transistors we have on our single chips. So this is actually called Moore's law. That has been, explaining the trend from 1965 almost. For years, we were able to actually improve the performance of our chips while staying within power budget. And that we were doing that by Dinard scaling. So Dinard scaling was a mean for us to, while we were getting our transistors smaller and smaller and putting more and more of them on the chip, we were able to keep their power consumption within a budget. And by doing that, we're actually we're increasing the performance of our chips while staying in the power budget. Unfortunately, around 2004, I think 2004, 2005, Dinard scaling ended. And what happens was that as we started getting our transistors smaller and smaller, they started leaking power. So we started having power leakage, and power leakage became a big deal, and made us slow down a little bit. And as a result of that, computer architects started thinking out of the box. So now that we can't make a single processor faster, let's have more of them. So this is a trend that you can see around 2004. We started having a lot of cores on our chips. So, and this trend also, unfortunately, has started to plateau because we have hit the dark silicon era. And it has been shown that even though we have a lot of cores on our processors, at any given time, we can't turn all of them on and run them all at full frequency. That also melts our processor. So we've not dealt with the power wall. We just turned the problem from transistors to cores, and we're still there. So we're still dealing with this. Something that you can't see in this graph is the surge in what is called specialized hardware. So nowadays we're actually designing hardware specific to applications. Like you have tensor processors for TensorFlow applications, for instance. So that makes us keep up with the performance of that specific application while staying within the power budget. This is another graph that shows basically what I just had in the previous one. So this is the performance of a single processor, the speed up we get compared to VAX11. As you can see, we're here, and we're not. The performance is not improving by much. So this is a modern processor. We'll come back probably to this and explain it a little bit more. This is Intel Haswell E. As you can see, it has 8 cores, a big shared cache, a memory controller. This is a spec for Intel Xeon Platinum. It has up to 56, I think it has 56 physical cores. So this is the trend I was talking about. We have a lot of cores put in our processors. This is an AMD EPYC, and it has 64 cores. Okay, now let's talk about memory hierarchy, something that we will again touch upon later on in the course. So there are 2 trends with memory hierarchy. So one is a smaller, faster, and larger, slower. And the other one is a smaller, costier, faster, costier, and a slower, cheaper. So as you go down this graph, you're going to get more capacity. But as you get more capacity, the speed is going to go down, and the price per, let's say, megabyte or gigabyte is also going to go down. So it's going to get cheaper. So the further in this graph you are, the first one being registers, these are very close to the processor. So accessing these take really low overhead, has really low overhead. After registers, you have L1 cache, L2 cache, and L3 cache. But then you have to also keep in mind that they are small. And as you go further, you get more capacity, but the trade-off is basically performance. These are the numbers that any computer engineer should know or have a sense about. You don't need to really know exactly these numbers, but you have to have a sense about the order of magnitude that these numbers are different. So if you want to access your cache, L1 cache, it's going to take 0.5 nanosecond, the first one. Going further, like if you want to lock a mutex, that's going to be about 25 nanoseconds, right? Now, an order of magnitude more would be basically something like compressing 1 kilobyte with ZP. And an order of magnitude more than that is going to probably be when you go to the disk. And then if you're going to send a packet from California to Netherlands and back to California, that's going to take what you can see over there. So 150 million nanoseconds. So you see the order of magnitudes that these numbers are different. So if you're going to just click on your keyboard and are wondering how long it takes, it's about 100 milliseconds, so something between 20 million nanosecond and 150 nanoseconds. The other trend that we have to pay attention to is the I/O network and memory bandwidth trends. So here on the x-axis, you have a year from 1990. I think it starts from 1995 to 2020-ish now. And the green shows you the DRAM bandwidth in gigabyte per second. Pay attention to these. So this one is gigabyte per second. You have the network all the way top that's in megabyte per second. So keep in mind that gigabyte is 1,000 megabyte. And then you have also your devices, SSD, that runs in between these two, and that one is also megabyte per second. What is important actually is not exactly these numbers. What is important is the gap between them. So the growth in memory bandwidth is also, this seems to be plateauing, whereas network and I/O, network and disk, they're going up with the same trend. Whereas memory is basically plateauing, and there seems to be a gap now between the two. Memory is still better because we're talking about gigabyte per second, not megabyte. But again, what we're interested in is in the slope of these two, and that has implications when you want to design systems. The other trend that is very interesting to look at is basically people to computer ratio trend. Again, on x-axis you have the years, on the y-axis you have the ratios. When we started back in years ago, we had one computer per, let's say, a million people. So you had a big mainframe that everybody was using, right? And then nowadays we're here where you have, each person carries multiple devices. So you have your Google, you have your smartphone, your tablets, your let's say your laptop, your personal computer, a lot of intelligent devices inside your house or whatever. So everything is becoming a computer, and every user is having a lot of them. We still have these sort of equivalent of mainframes. We still have data centers, massive data centers, where you get to use a system that is used by millions of people. But at the same time, we're also having these streaming devices. So basically, this trend is also very interesting when you're designing when you're designing operating systems. So in early days, you had a computer that was basically used by a single user at any given time, and that single user had complete control over all the hardware. And OS was not really an OS. It was basically something like a runtime library that would get attached to the application and would, facilitate using the hardware. And after that, we got batch systems. So the thing about the first model was like after one user would leave, the whole system would come down. The second application would be loaded, and then the system would get started and run that system, that new application. But switching between the users, the entire system was idle, and that was wasteful. So what they came up with was, why not like keep a waiting queue? So everybody comes in, they submit their tasks, and then once one task is out, I just immediately bring the second task in without having to spare idle cycles. And from there, we got to multiple users per computer system. We got to multi-programming. We got to interactive performance. We got to do time sharing. So at the same time, multiple users nowadays are using the same system. So when you, for instance, SSH to let's say ECE Linux, at the same time, multiple users might be accessing that same server, and that's what we're getting right now. So you see the trend here. Complexity now. This was about hardware, the trend in operating system. Now let's talk about complexity. Well, applications have different modules, and they run differently on different devices. They might be implemented differently for different hardware. So the same application, if you want to run it on ARM processor, you might want to implement it differently than you want to run it on a server. And they actually fail in unexpected ways. And they could be attacked. And there are malicious people out there. So it's usually not feasible to test your hardware, although there has been a lot of work to make it easy to test the hardware and mathematically prove that your software works perfectly. But usually that's not the case. Usually we're not able to test our software on all possible environments, on all possible hardware that could run it. So bugs could happen. If you look at just Linux kernel over the years, this is how many lines of code in Linux kernel we've had from version 2.6 to version 4.19. So this trend is not going to go down, right? So the complexity of Linux kernel is going up. And that's basically one evidence for what we've already known about the complexity going up. I just realized that I don't need my picture to show here. Okay. Now, how do we tame complexity? So every piece of computer hardware is different. You have different CPUs. You have different amounts of memory, different types of hard disk drives. You have different devices, different types of devices, different types of keyboards, different types of cameras, you name it. So there are questions now we have to ask. Are we asking programmers to write different programs for different hardware? Is that what we're seeing? Do we need to alter our programs for every new piece of hardware that comes? Like, let's say tomorrow Intel is gonna, let's say, introduce a new processor. Are we gonna go back and change all the applications we wrote? If we have an application that is faulty, does it usually crash the entire system? So hopefully, and we can ask these questions more and more, hopefully the answer is no. And that is the beauty of operating systems. Again, coming back to that picture where we were in the middle, we have been able to mask most of this from the stock, most of the trends that are evolving inside hardware from our applications. And we have been able to successfully protect and isolate faulty applications to themselves, not letting them hurt other applications or the operating system. So in summary, we talked about operating systems providing virtual machine abstractions. We talked about operating systems' job to coordinate resources, to protect users. If you remember, operating systems were the role of operating system was to perform, to be illusionist, to be a referee and to be a glue. And in ECE 350, we're going to see a combination of ideas from different areas of computer science, from algorithms, from computer architecture, from you name it, data structures, and such languages, programming languages. So yeah, that would be the first lecture. Now I'm going to move on to the second one. If there is any questions, please feel free to ask. Okay. So I got a question, is every running process a process VM? Could a system VM contain many process VMs running within it? Yes. So every process is the job of the operating system is to provide that abstraction. So every single process is that abstraction, is a process VM. Now, again, you have different levels of protection that you can provide, and that's how different operating systems are different. And for system VM, yes. So within your VM, within your virtual machine, you can run multiple process VMs. So let me publish this one. Oh, thank you for asking this question. So somebody's asking, are the slides on ECE 350 website updated? Yes. So before so I'm going to put the slides as I'm going out, but then right before the lecture that I'm presenting, I might change really small pieces of it. So, I mean, I don't know why it could be that you're downloading it from now, from 2 weeks, 3 weeks from now, but always it's good to download right before the lecture so that you get the most up-to-date version of the slides. I'm not making a lot of changes. I'm making like a little bit of changes. So thank you for asking. Oh, I think that's okay. So let's keep going. Let's start lecture 2. So this is the outline. We're going to talk about a brief history of operating systems. I might actually skip over this part and let you. I've put a bunch of videos online that talk about. Sorry. So I put a bunch of videos that would talk about like history of some of these operating systems. So once that's done, we're going to talk about 4 fundamental OS concepts, naming threads, address space, process, and dual mode operation and protection. You should know already about threads and processes. We're going to talk about things that you probably didn't go deep into in ECE 252. So let's go ahead with it. So if you look at the operating system design, there have been several distinct phases. So at the beginning, you had really expensive hardware, and human being, meaning programmers, were cheap. So this is a very famous quote from Thomas Watson the chief of IBM who said, I think there is a world market for maybe 5 computers in 1943. So that's an interesting thing because he's often called the world's greatest salesman. He actually sold, I think, I don't exactly know, but he sold 5, 6 of them already. So after that, we had a phase where you had the hardware became cheaper and human programmers became a little bit more expensive. That's where you got your PCs, workstations. It was the rise of graphical user interfaces. And these days, hardware is really cheap. And programmers are really expensive. So this rapid change in hardware has led to also changes in operating systems. So as we talked about, we went from batch execution to multi-programming to time sharing to having multiple users at the same time using the device to right now, Internet of Things, where you have multiple operating systems and multiple devices at the same time. So yeah, you get a variety. So when you have really a small device, you don't really want to put millions and billions of lines of code. So you have operating systems that are really small, and you have operating systems that are really huge. So these are, I'm going to jump on this one. So this is the archaeology of a bunch of lines of operating systems from, BSD Unix, Apple OS X. You can go back and see what the ancestors were. You have here Ubuntu, Debian. They come from Linux and Minix, and you can just see this last line. I'm not really interested in, but anyways. The other thing to pay attention to is the difference between monolithic operating systems versus microkernel operating systems. So this happened a while ago. People were just thinking about, maybe microkernels are better. The reason people started thinking about microkernels was basically because of the complexity of operating systems going up and up and up. So you have this kernel that is ever growing, it's complex, and because it's basically in charge of your hardware, you don't really want it to be faulty. Sorry. Because if you have a faulty, oh, I still have my picture here because I didn't send it to the live. Sorry about that. Okay, now you don't have me. Good. Okay, so yeah, when your kernel is huge, there is a higher chance of fault happening inside. And if you have a kernel that is faulty, well, your entire system is compromised. So people started thinking about really making the kernel the bare minimum that you really need. So basic inter-process communication, basic virtual memory, basic scheduling, and then bring out every other functionality inside the user space. So on the left, you have the monolithic kernel model, where your device drivers are basically running inside the kernel mode. Most of the services that you have are inside kernel, whereas in the microkernel, it's really bare minimum and minimalist. and you bring everything else as a functionality inside your user mode. Now, not many operating systems, mainstream operating systems, really picked up this idea. I got a question in my is all the other application code required to be built by third-party companies? So I got a question, I'm not quite sure if I understand it correctly. So it's asking, somebody's asking, is all the other application code required to be built by third-party companies, organizations? So as far as I understand your question, most of the applications are assumed to be implemented by third parties. Even device drivers nowadays are implemented by third-party companies and organizations, and we don't have any choices but to run them. So like if you have, for instance, a GPU, an NVIDIA GPU, the driver is not open source, and you're still running it. It's a third party, but you don't have any other choices. You have to run it. Anyways, so let's move on. Now, microkernels didn't really find their ways into mainstream operating systems and kernels, but they definitely influenced the kernels, the mainstream ones. So the main problem with microkernels, although they're really good in providing modularity, security, fault tolerance, but they provide really, they require a lot of inner process communication between different modules. So every time you go from kernel to user space and come back, that's a very expensive process. And with microkernels, you have to do this a lot because many things that used to be running inside kernel mode now are running inside user mode. And you have a lot of communication going back and forth between the user mode and kernel mode, and each one of them is really expensive. So overall, the whole thing will be expensive. And in a day and age where performance is #1 issue, people really didn't like the idea. But again, it actually influenced us. So many operating systems now provide some services externally. They don't, for instance, OS X, Linux, the windowing is now running outside the kernel. Something that, again, we talked about previous lecture, that is the glue part of the operating system, but it's not implemented inside the kernel. And some of today's monolithic operating systems used to be actually microkernels, and they transitioned to monolithic over time. So let's just start with the first 4 fundamental OS concepts, which is threads. We're going to start by just looking at how an operating system is booted from the beginning. When you turn on your computer, what happens? So usually, this is usually the case in most cases. In most x86 systems, you have BIOS that is stored on a very specific hardware called boot ROM. This is a very fast memory. It's small, very fast. The property that boot ROM has, it's that it's expensive to write. It's basically ROM is a read-only memory. So you still can write in it, you can update it, but it's very expensive to update. Now, usually we put BIOS on ROM. So the moment you start your computer, the BIOS code starts running. And what it does, it copies the bootloader from disk to memory. So it has to know where bootloader is. It brings bootloader to memory and then jumps to the first line of bootloader. and start running bootloader. And what bootloader does, it should also know where the OS kernel is. And then it goes and copies the instruction and data of the kernel, put it in the memory, and then jumps to the first instruction of your OS. And once that happens, then OS takes control and then starts running applications one at a time, usually with one application that would allow users to initiate other application, let's say the login application. So now a couple of questions. I'm going to wait. I pose the question, I wait a little bit, and then so that you can also think while I'm giving the lecture, and then I'll answer the question. So why not storing the kernel on the boot ROM? From the beginning, why go through 3 levels of indirection, a BIOS, bootloader, and then OS kernel? Why not just from the beginning just bring up the OS? So the answer to that question lies in to the fact that the boot ROM, first of all, it's small. It's not a big memory. Second, writing into it is slow. Usually, when you have operating systems, they get updated pretty frequently. And it's really hard to basically do all these updates into the ROM, which is a read-only memory. The second question you might ask, okay, sure, why not now, instead of bringing up bootloader, why not bringing up kernel? So BIOS, instead of bringing up bootloader, why not just immediately bring up the operating system? Again, I'm going to wait a little bit, think about it, see what comes to your mind. The answer to that is by another question. What if we have multiple operating systems? What if on the same system you install multiple operating systems? Which one should the BIOS bring? So you see that, well, you really need this one other level of indirection. The other answer to that question is also BIOS just reads blocks of data from disk. It doesn't know the file system. It just needs to know I need to read these many blocks from disk. Whereas the bootloader now, once it comes up, it has more code. It can actually interact with the bootloader. It has to bring up the files, the operating system. So it works with the file system. Got a question. What's the definition of bootloader? So I'm going to define bootloader as basically its functionality. The functionality of bootloader is to bring up an operating system, copy the code and data of an operating system. It's usually, if you have, for instance, usually those who have a system with one operating system, they usually don't see the bootloader. If you had, let me first publish this. I used to have actually a system where I installed Linux and Windows and stuff. So the first thing I would see was the bootloader that would ask me which operating system you want to go to. So I would, choose, oh, I want Windows, or I want my Linux to come up. So that's the job of the bootloader. Hopefully that helps. Okay, so now operating system is up, running. Where am I? Time. Okay, I'm gonna give you guys 2 to 3 minutes of a break. I will continue in 2-3 minutes. So 1:55, I'll continue. I'm gonna just yeah, this is a break. So get up, stretch yourself, and then come back in 3 minutes. And in the meantime, if you have any questions, definitely use the Q&A. So what is that? Is the bootloader stored in RAM? So bootloader, let me publish this one. Bootloader is stored in your disk. The BIOS knows what it is, where it is, so it just reads a certain number of bytes. I used to know how many bytes it is. I think it was 256 bytes or something. I don't remember. It basically knows how many blocks of data it has to read. So it reads from disk and brings it to DRAM. The same with operating system. So operating system resides, the code and the data reside in the disk, and then the bootloader reads from disk, brings it to the DRAM. Okay, we're back. So let's get going. So what is the bottom line? The bottom line is that we want to run our applications. So you have a programmer that would edit their code, their source code. Then they would compile and create an executable image. This image has the data, the instructions that the hardware is going to run. Now, what operating system does is to bring that data and the instructions to the memory. So we load the instructions and the data into the memory. I got a question. I'm a bit confused by what you mean by raw bytes. Yeah, so basically, let's say you have, so we'll talk about file system in more details, but so the question is asking about what's the difference between how BIOS interacts with the hard disk, whereas how the bootloader interacts. So you could just, if you remember, I don't exactly know if you guys have covered this. So you could just read blocks of data without knowing what they are. So you just read from the disk raw blocks, copy them, and you're done. You don't need to know what they are. Whereas when you're talking about file system, you actually know, okay, this first bytes are the headers, inodes, whatever. They have information that shows me like this is a pointer to that is a pointer. So you know some information about the data that you're reading. So you interact with the file system, whereas you just read bytes out of disk, not knowing what they are, what they represent. Is bootrom usually on the motherboard? Yes, it's basically part of your hardware. Okay, hopefully that answered the questions. Now, so the first thing, operating system loads instructions and data segments to the memory. Next, we need to create stack and heap for our programs to run. Then the operating system transfers control to the program. If you remember from the first lecture, we had the registers inside the processor that would read their information, that would update their information from the memory of that particular program. And this is the job of operating system, to now basically make everything, every pointer to point to the memory that is allocated to this program. And while the program is running, in the process, the program might ask for services. Again, going back to the first lecture, you might want to interact with the network. You might want to read a file that is stored in the disk, so other hardware. So you're going to ask for help, and that is provided to you with system calls. We'll talk about them. So while the program is running, we're going to provide services. And we're going to do all of this by protecting ourselves, the operating system, from the program, and protecting other programs from the running program at the same time. So this should be a familiar graph for most of you. What happens is, so you have your instructions and your data. Your program counter is going to point to an instruction that should be executed at this cycle. You reference the memory, you bring that instruction to the processor, you start fetching it. So this process was fetching, so you fetch the instruction from the memory, then you decode the instruction to see what it is. Is it an add? Is it a jump? Is it a multiplication? Is it a divide? Whatever it is, we need to decode. Once we decode, we execute it. So it might be executed using the registers. So if it is an add, it's going to add 2 registers and then store the result back to another register. And potentially, if it is, let's say, a store, it's going to store the data back to memory. Or if it is a load, it's going to load the data from the memory to the registers. Now, if you look at this graph, every instruction that we execute, at least we access memory once, at least, to get the instruction. So at every cycle that we execute an instruction, for executing even one instruction, we have to access memory. So we have to deal with memory a lot. That's the bottom line. And sometimes more than once. If it is a load or a store, we might actually access memory multiple times. After we execute, the next is to see what is the next instruction. So we update PC. Now PC should point to the new instruction. If we're going through a bunch of instruction, now PC should be next one. If it was a jump, now PC should point to the jump. If it was a procedure call, now PC should point to the beginning of that procedure. So here is in details what happens. So we fetch, we decode, we execute, and we write the result to the registers or back to the memory. And then we say, what is the next PC? And we repeat this again and again and again. Yeah. So what are the threads? This should be a recall for everyone. So thread is a single unique execution context. By context, we mean everything in the registers and everything in the memory. So your program counter, your register, your execution file, the flags, your stack, your heap, etc. So everything that represent that execution context is part of the thread. So a thread is executing on a process that it resides on, its registers. So the moment the register in the process, the processor point to the memory space, the address space of a thread, and start executing instructions of that thread, we say that thread is executing on the process. So what are the registers? How many registers do we have? Do we need to know all of this? So this is going to be the instruction set architecture that defines what are the registers that you have, and this is different from architecture to architecture. So different architectures have different registers, and that's why you have a compiler per architecture. So your compiler should know on which architecture you want to run your program. That's how it internally figure out how to load the registers. I'm not going to put more time on threads. Hopefully you know all about threads. The second OS concept is address space. So what is address space? Let's go through a bunch of definitions first. So address space is basically a set of accessible addresses and their state. Easy. So set of addresses and their state, basically what is in them, would be address space. Now don't mess this up with your physical memory. So physical memory is basically a data storage medium that we call like DRAM. That's your physical memory. That's not an address space. Now you have, for your physical memory, you have physical addresses. So every byte inside your physical memory is addressable. That's why you have physical address space. That would be a set of addresses that are available on your physical memory. Let's say if you have a system that has 4 GB of memory, that has basically that translates to 2 to 32 bytes. So hopefully everybody knows that. Let me try this fancy stuff. Let's see if it works. Maybe it was not a good idea to do this, but let me see if I can get it done. Sorry about that. Yeah, never mind. I was trying to use my tablet to do some stuff, but it just doesn't work. Okay. Sorry. That was a fail attempt. Anyways, so every gigabyte is 2 to 10 megabyte, and then every megabyte is 2 to 10 bytes. And that's how you, sorry, every megabyte is 2 to 10 kilobyte, and then every kilobyte is 2 to 10 bytes. That's how you get 2 to 32 bytes, which is basically 4 billion addresses. Now, another thing here is virtual addresses. So this is basically a set of addresses that are generated by program. Now, this depends on your processor. So if you have a 64-bit processor, your programs that are running on this processor could potentially create 2 to 64 different addresses. And that is more than 80 quintillion addresses, 10 to 18. I had to search Google to get this quintillion. So again, this slide is important for everyone to distinguish between virtual addresses, physical memory, and the concept of address space. So we introduced physical address space and virtual address space right here. Now let's look at the virtual address space layout of a C program. This is basically how it looks like. From the bottom, you get the binary code. This is the instructions for each program. Then you have the initialized data. Then you have uninitialized data. And then your heap starts here and grows up as you dynamically allocate. And your stack starts from the top and grows downward as you, let's say, do function calls iteratively, or yeah, basically the stack is used for function calls. It grows this way, and then you have command line arguments and the environment variables residing on top in a reserved space. So if you look at this program, for instance, this is one program. If you look at it, then you can see that, okay, this is an uninitialized data, so it's going to be there. Y is initialized to 15, it's going to go there. Then the arguments of your main function are going to reside at the top. So these are the variables inside your function. They're going to reside inside the stack. Here you're dynamically allocating memory. It's going to go to your heap. And your entire code is basically the text of this code is going to be inside your binary code. Now, this is a very important example of a stack and how it grows as we call functions. So please pay attention to this example. It's an important example that we will need as we go. So here I have a program that before doing this program, I actually want to show you something, like an example with Linux. I know it's going to take some time, but it might be worth it. Okay, so I'm now in a Linux system. Hopefully you guys can see. So let's see what is the PID of bash. P. Sorry, PID of bash, it's 257. Okay, now if I look at proc 25740. So this is basically the bash, the program that I'm running. Basically, I use SSH to connect to my server. Now, if I look at memory map, mmap, I think it's maps, yeah. So if I look at maps for this bash, this is what you get. So if I were to just, if we look at this, the first, so this is upside down from least, from the start of memory to the most significant bits of the memory. So at the bottom, you see the code for bash. Then I have the heap. So it's showing me from this address to this address. These are virtual addresses. My heap resides. And then in between, I have a bunch of shared libraries between my heap and the stack. So a stack is here. And this space is used for virtual system calls and such. So this is just one example to see this in action. If you want to see what each one of these mean, you can do man proc, and then go to maps. So basically, the first one is the address, then the parameters showing if it is read only, write only, I can execute them, whatever. The offset, inode, we will talk about them. These are related to the file system, and this is the path name for each one of them. So that was the layout, memory map of bash, basically. I just ran. Okay. Okay, so now let's look at this stack example. So here is the code. I have a function A that is going to have, it has an if, given the input, it's going to make a decision to call B. So if temp is less than 2, it's going to call B and print temp. And then I have B, which is going to call C, and I have C, which is going to call A2. Yeah, I think I made this. I think it's if temp less than 2, then B, else, and then after that, if is print TMP. We'll see it actually as we iterate. Suppose that we start by executing A1. So we're going to call A1. Let's see what happens. So when you call A1, what do you have on top of your stack? So you're going to get, so on top of the stack, you're going to get the arguments to this function, which is 1. So you're calling your function by 1, it's going to get on top of your stack. And then you're going to have the return address. Once this function is done, where should I go? So we're always returning to the address after the function. So once we're done with this function, we're going to come back to this exec. So we put the return address here. By the way, I'm going to go ahead and finish this lecture after 1 hour and 20 minutes, which would be like 3 minutes or 4 minutes after 2:20. So if you want to leave, definitely leave, but I want to have 1 hour and 20-minute lecture. Sorry about that. I started this lecture 3-4 minutes late. Anyways, so let's see what happens. After this, we're going to come to A, check if temp is less than 2, which it is. So we're going to call B right after the temp. So here is another function call. It doesn't have any argument, So we're going to just put the return address here. So there's no argument. And the return address, we're going to come back to the next line after B, which is A3. So we put the address of A3 on top of the stack. So the stack is growing. Now we go to B, we're calling C. Again, it has no argument. We're going to come back to B2. So we push the address of B2 on the stack. And well, we go to C because we just called C. Now inside C, we're again calling A with argument 2. So somebody is asking what is return. So return is basically the return address. It says, once you finish this function, where should you go? So the return is basically when you do a function call, the return address is the address right after that function call. So for instance, let's look at it here. We're calling A2. So we're going to push 2 things on the stack. The argument is 2, and the return address is the line right after this, which is C2. So we're going to push temp equals 2, and return address is C2. Now we're back to function A. Now we're going to check if temp is less than 2. Well, it is not. So this last time we look at the stack, the temp in the stack is 2, top of the stack, right? And 2 is not less than 2. So we're going to print the TMP. So we're going to print 2. Now we're done, right? Next line is A4. So we want to return. Where do we return? We look at the top of the stack to see where should we return. And the return address on top of the stack is C2. So the next instruction is going to be C2. Okay, well, C2 is also a return. So it's end of a function and we want to return. Again, where should we go? We look at the top of the stack for a return address. And here the return address is B2. So next instruction is going to be B2. Well, B2 is again a return instruction. We're going to come out of B. And then where are we going to go? We look at the top of the stack for a return address. And that is A3. So we're now going to go to A3. We have a print temp. OK, what is temp? We're going to look at the stack to see what temp is. Temp is 1. So here is where we print 1. So after 2, now we print 1. And we're done here. So again, we're returning from A. Where should we go? Well, we look at the stack. Stack says go to exit. OK, we go to exit. Hopefully that was clear. So this is basically how stack grows and what are the arguments on top of the stack. The third OS concept is process. Again, you should know about this. We're going to define process by the 2 first concepts that we saw. So a process is a combination of an address space and bunch of threads, 1 or more threads. Each process has its own address space, its own file descriptors, its own file system contexts, and that's how we provide isolation between processes. Why do we want to have processes when we already have threads? Well, there's a fundamental trade-off between protection and efficiency. So within processes, we're going to enforce protection. We're not going to let one process to access the data of any other process. But within a process, we're going to allow threads to communicate freely with each other. What that means is we're not going to enforce any protection when it comes to threads. So I think I've reached the 1 hour and 20 minutes. So I got one question just to clarify. There is a difference between the call stack of a program and the stack of a function. So if you're asking about, I'm not quite sure if I understand this question clearly, but basically any process has a stack, or any thread has a stack, as you can see in this picture. So if you have one process with one thread, you only have one stack. So your processor provides you with a stack pointer. So that stack pointer, every time you call a function, you're going to use that stack pointer to push stuff on it. So you have one stack, and every time you call a function, you're going to use that stack to store the return address, to store your variables. Hopefully that's what the question was asking. If not, definitely shoot me an email for more clarification. So with that, I'm again sorry to go over time. It's now 2:24. We'll continue on Friday from here. Thank you.